So we have talked about transportation problems, and now we're going to look at another types of problems, but these problems actually still related to the transportation problems. They are called assignment problems. Assignment problems are special cases of transportation problems, which means that if you want to use the transportation simplex to solve assignment problems, you can do it actually. But there is an algorithm to solve assignment problems, which is simpler and more efficient than transportation simplex. So that's why we're going to learn this problem separately, because there is a special algorithm as well to solve this assignment problem. And that algorithm is called the Hungarian method. Okay, so let's start. In this case, machine code has 4 machines and 4 jobs to be completed. Each machine must be assigned to complete one job, and then the time required to set up each machine for completing each job is shown in this table. And machine core wants to minimize the total setup time to complete 4 jobs. Use linear programming to solve this problem, okay? So first, we're going to model this into linear programming and see how it looks like. So our decision variable is a 1, 0 variable. Xij equals 1 if machine I is assigned to do the job j, and Xij is 0 if machine I is not assigned for doing the job j. So you see the sign restrictions here is Xij is either 0 or 1. The objective function is to minimize the total setup time. So 14 times x11, 5 times x12, and so on until 6 x43 and 10 x44. Similar to the transportation problems, we have machine constraints here. You can think of this as the supply constraint in the transportation problem. But you see that each machine can only supply one unit. It means that one machine can only do one job. And for the demand point, we have the job constraints here, and the demand equals 1 because one job only requires one machine. So this is the linear programming formulation for the assignment problem. You can see it's very similar to transportation problem, except that now the supply capacity for the supply points and the demand for the demand points, they are all equal to 1. Another thing is the Xij only allows the value of either 0 or 1. As I said earlier, you may solve that problem using transportation simplex, but it is not very efficient. So somebody came up with the method that is called Hungarian method. So let's see how we are going to do this step by step with an example. Before we go to the example, there are 2 important remarks here that I'd like to talk about. First is that if the problem is a maximization, then you can still solve it. This is how you do it. You multiply all the profits in the matrix by -1. So now they become costs, and you would like to minimize the cost. Okay, so multiply the profits by -1, and then you can solve the problem as a minimization problem as usual. The second one is that if the number of rows and the columns in the matrix are unequal, for example, you have more machines than jobs, or you have more jobs than machine, so what you can do is that you may balance this problem by adding dummy points, either dummy machine or dummy job. And then after you do that, after you balance the problem, then you can solve the problem using the Hungarian method that we're going to start talking about in the next slide. Okay, so pay attention to these 2 remarks here. Okay, so let's go back to our example. So we have 4 jobs and 4 machines, so it's already balanced, so it's okay. What we need to do first is subtracting from each cost the minimum cost in its row. So find the minimum cost for each row. For example, the first row, the minimum is 5. The second one, the minimum is 2. The third one, minimum is 3. And the last one, minimum is 2. Subtract each row with its minimum. So now this is how the first row looks like. Okay, so this is 14 minus 5 becomes 9. 5 minus 5 becomes 0 in the new table, and so on. Okay, just convince yourself that this new matrix comes from the old matrix, and we subtract each row with the row minimum. Then for the next thing we do is subtract from each cost the minimum cost in the column. So now do the same thing, find the minimum cost in the column. So for the first column, the minimum is 0. For the second one, the minimum is 0. The third one, minimum is 0. The fourth one, the minimum is 2. Then we subtract each column by its minimum. The first, second, and third column, obviously they don't change because the minimum costs are 0. But the fourth column, you see, from 2 becomes 0, from 3 becomes 1, from 6 becomes 4, and from 8 becomes 2. So that's the end for the first step of the Hungarian method. For the second step, we need to draw the minimum number of lines. The line can be horizontal, vertical, but cannot be diagonal. Okay? And then we need to find the minimum number of lines that cover all the zeros in the matrix. So let's see. So these are the minimum number of lines. We need 3 lines to cover all the zeros in the matrix. Remember, we need to find the minimum number of lines. So the minimum number of lines is 3. This line, they cover 2 zeros here, and then this line, it also covers 2 0, and we must add that line to cover the other 0. Because our number of lines equal 3, but we have a 4 by 4 matrix, so this is not an optimal solution. The number of lines are 3, but our matrix is 4 by 4. So we have m lines which is fewer than, we have lines that are fewer than m. In this case, m equals 4. We have 4 jobs and 4 machines. So we go to step 3. So in step 3, we find the smallest non-zero element that is uncovered by the lines. So here, if you look at the uncovered elements, you see that the smallest non-zero element equals 1. Okay, so these are all uncovered elements, and among these uncovered elements, the smallest non-zero element is 1. So k equals 1. And then what we need to do is subtract k from each uncovered element. So 10 minus k, 4 minus k, 1 minus k, 2 minus k, 4 minus k, and 6 minus k. And then we add k to each element that is covered by 2 lines. Okay, so that's why we have 9 plus k, because you see 9 is covered by 2 lines. And then 4 is also covered by 2 lines, horizontal and vertical. So these two numbers, 9 and 4, we will add k to these numbers. Okay, and here's the result. You see that 9 becomes 10 now, 4 becomes 5, while on the other hand this 10 becomes 9, and so on. So the uncovered elements are, we subtract them by k. the element that is covered by 2 lines, we add them with K. So here's the new matrix. We go back to step 2. In the new matrix, again, we try to draw minimum number of lines that cover all the zeros. Here, the minimum is 4. We cannot do less than 4 lines. So it means that the minimum number of lines that we get is 4. Our matrix is 4 by 4. So we have obtained a optimal solution. So how can we interpret this solution? Well, you say that job 3 should be given to machine 3 because you see that in this column there is no other 0. So job 3 for machine 3. Okay, and then let's see if, okay, here's another unique 0 in this row. So we should give machine 4 doing job 1. Okay, machine 4 doing job 1 because in this row we only have 1 0. 0 is like the best pair of machine and job. So if one row only have 1 0, then we must give that 0 to the corresponding machine and job. Okay, so and then next, because job 1 and job 3 has been performed, now for job 2, this is the only unique 0 in this column. So we must give job 2 to machine 1, and finally we must give job 4 to machine 2. So that's how you reach the optimal solution for the assignment problems from the output of the Hungarian method. Okay, so that's the end for this topic about assignment problems. Next one, we're going to talk about transshipment problems. So see you on the next one, and thank you.